started.
Okay.
Before they began. I'm writing the code for it. I gotta get.
Open MPLabX. That's a good start. And then write a program that reads from port A and copies that value into some file register. And just put that in the loop, just say go to the beginning again. So 3-line program, move port, or 2-line program, move FF port B, comma, some file register, and then go to the beginning again. Put that in the simulator, assemble it, go into the debugger. Set a breakpoint at the beginning, set up stimulators for port B, set up watch points for where you're moving port B into, and watch what happens. Use those stimulators to set port B, each bit either high or low, execute your instruction and see if it copies the right value into memory. And then, if it's not doing that, think about the tri-state registers, right? And play around with setting up the tri-state registers and get a feel for what those are doing. And that gets you the basic input mechanism from the pins into the file registers. And then play around with output. Write a 2 or 3-line program that tries to output dead beef. Well, that's too many bits. Tries to output some 8-bit pattern to port B. Right, so move a literal into W, move WF into port B, go back to the beginning and do it again. And step through that and see if port B gets set. And it probably won't, and you're going to need to play with, again, the tri-state B registers and probably add con1. But once you get that working, you're getting more fluent with the debugger and you've got the basic I/O mechanism down. And that gets you probably a quarter of the way through the real hardship of this program. And then start thinking about, okay, so now I've got a number that I've read in from port B, I want to break it up into 2 numbers. I don't want a single 8-bit number, I want these 2 bits to be one number, but I want these 2 bits to be a second number. And see if you can come up with some code to pull those 2 bits out from, you know, those 3rd and 4th positions and turn it into something that just looks like a number between 0 and 3. And once you've got that working, now go ahead and add those together. And do all this in the debugger, don't even touch a circuit board, right? Do this in the debugger, get that working, and then just keep building from there. And I can work with you on those initial steps in lab if you want.
Okay.
Debugger is definitely your friend on all this stuff because it removes all of the hardware issues, all the programming of the chip issues, and bad wires and all that other stuff. And lets you concentrate on the software. But there's 3 things going on now in these labs we're doing. At least 3 things. One is coming up with an algorithm. And we need some sort of algorithm for how we're going to take port B and break it into 2 numbers, add them, put it on port B. So there's coming up with the algorithm, which is a programming 121 type challenge. There's converting that into assembly language, which we're going to work on now. And then there's building the hardware circuit. And then there's getting it all together, right? It's getting your program into the MPLab environment and assembling, loading it onto the chip and all that stuff. So there's a number of different pieces to this now. But they're the same thing over and over again for the most part. So it'll get easier over time. So let me go through these extra branch statements and then let me go through some examples of algorithms and converting them into assembly language. And then if there's questions on Lab 2, coding and such, as we go through this, bring them up along the way. But this should all kind of tie in. So let's talk about these conditional branches first. Yeah.
With the quiz coming up for the chapter, a whole lot of the examples and things in the chapter were translate this to machine language or translate this from machine language. Is that going to be?
That's a big part of it, yeah.
Okay.
Yeah, so it's mainly going to be that, maybe some sort of general questions related to what you've done in lab. some of the stuff we're doing here and that you've been doing on lab 2 as far as taking some short piece of pseudocode and writing assembly language for it. So our questions along those lines. I have to actually write the thing still. All right, so we talked about skips. We can use skips to do conditional execution, but it's kind of a weird mechanism because you can either execute the next instruction or not execute the next instruction, and you have to somehow work that machinery into doing what you want to do. But if we've programmed in other languages and we've done flowcharts, we usually see something like this. We get to a point in our flowchart and there's some condition that we test. And if our condition is true, we go down and we execute a set of code here. If the condition is false, we come down and we execute a different set of code. It's a branch, right? And typically, so let's say we do A, B, C, and over here we do D, E, and F. And then we do H, I, J. So if the condition's true, we do A, B, C, and then H, I, J. If the condition's false, we do D, E, F, and then H, I, J. And what we kind of, and it's a little hard because we don't really talk about go-tos much anymore in C, even though you can write go-tos in C, and you should. But we have to use go-tos in assembly language, right? We use jumps all the time, and a for loop or a while loop uses a go-to to implement it. But here's what this would look like if we were thinking in the language of go-tos. So if condition go to, I don't know, I'll just call it label false. Otherwise we say A, and then B, and then C, and then go to label continue, and then over here is label false, which says do D and E and F, and then down here is label continue, which does H, I, and J, and Y skip G. But here's the logic, right? If our condition is true, we come down here. I did that wrong, didn't I? I don't think so. Condition is true, go to condition is true, we come down to label true, we do D, we do E, we do ABC. If the condition is true, we come down here, we do A, B, C, and then we do H, I, J. If the condition is false, we don't do this jump, we do D, E, F, and then we go to label continue, so we skip over A, B, C, we do D, E, F, and then H, I, J. So these conditional jumps, if some condition is satisfied through a branch, are pretty useful for doing basically if statements or if then else statements. Here's a simpler example. So if some condition is true, do A, B, C, and then do D, E, F. Just a plain old if-then, without an else. And this looks like this. So if our condition is true, we do A, B, C. And then we do D, E, F. So if we want to do this with a conditional branch, we could do something like this. If not condition, go to some meaningful label like skip 42. And down here we say do A, B, and C. And down here at skip 42, we do D, E, and F. So if the condition is true, we don't take this jump, we do A, B, C, and then D, E, F. If the condition is true, if the condition is not true, so if it's false, then we take this jump, we skip over A, B, C, and we do D, E, F. We can't do that directly with a skip statement because skip instructions only let us skip one line of code. And in many cases, we want to skip a whole section of code. All right, so there's a series of branch instructions that are built that are supplied to do this kind of conditional branching. And they work as follows. So they have forms like branch if 0, branch if not 0. Those are the two most common ones. So this checks to see if something is 0, and if it is, it jumps, it does a go to. If not, it just continues on to the next instruction. This one checks to see if something is not 0. And as long as it's anything other than 0, it takes the branch. So branch if 0, and branch if not 0. The question is, what is this thing that it's checking to see whether it's 0 or not?
rag, W-rag?
That would be a reasonable way to do it, but it's not what it does. But it's got to be something, right? Because we don't get to tell it what to check in here to see if it's 0 or not 0.
Whatever came before it.
Whatever came before it. Basically, generally the last thing that you did, if it resulted in a 0, then BZ will take the branch. And if the last thing you did not result in a 0, then BNZ will take the branch. BZ won't. So for example, if I say move LW 1, move WF, I don't know, let's just assume we have a file register X, and then decrement file register X, and branch of 0, blah. This puts a 1 in W, this copies W to X, so X is equal to 1. This decrements X, so X is now equal to 0. And now I say branch of 0, and the last thing it did resulted in 0, this is going to branch to blah. But if I move 17 into W, move that into X, decrement X, X is now 16, branch of 0, the last thing was 16, not 0, it's not going to branch. And typically we're doing either an increment or a decrement, or maybe an add or a subtract, or maybe a logical operation, an and, an inclusive or, something like that, and then doing a BZ, B not Z. Well, how does it remember if the last thing you did was a 0 or not? It's got to have some mechanism inside for keeping track of that. And it does. It uses something called the status register. It's a file register. It's a special file register, so it's stored between F80 and FFF. And its whole purpose for existing is to keep track of every time that an instruction results in 0 or not 0, or some other possibilities. So let's look at the status register. So it's an 8-bit register, right? It's a plain old file register. This bit right here, this is the 0 bit. This is the bit that it uses out of all the file registers available. This one bit's used to record whether an operation results in a 0 or not. And it's a little backwards-ish, because if the 0 bit is a 1, then the last operation you did resulted in a 0. And if the 0 bit is a 0, the last operation was not 0. But it's a flag, and usually when we have flags, we think of a 1 as true and a 0 as false. So a 1 here means the 0 condition is true, which means the last thing you did was a 0. 0 means it's false, so it's not 0. But we don't really need to know that usually. We can just say BZ, BNZ. And it will look in here and check out that bit and do the right thing. There's 4 other bits available in here. There's a negative bit, because remember the PIC uses 2's complement, so it understands positive and negative numbers as well as 0. And if your last arithmetic operation resulted in a negative number, this bit will be a 1. So if you want to do some branch, some number is less than 0, you do your calculation, you can say branch of negative. If you get an overflow, you add 2 numbers and your sum is bigger than 255, it doesn't fit in 8 bits, that generates an overflow. And the overflow bit will be set. So you can tell when your sum was too big. This is a carry bit. It's the same carry that we always deal with. If you add 2 8-bit numbers and you get a carry out of that 9th bit, that bit gets set. And this is called the decimal carry. This is a carry out of the 4th bit, bit 3. And we'll play around with that another time. The other piece of this is that not all instructions will affect all of those status bits. But there's an easy way to tell what affects what, and that's in this table 20-1. So for example, if I add the W register to a file register, here's the status bits that get updated. Carry, decimal carry, 0, overflow, and negative, all of them. If I do a decrement instruction, that updates all 5 status bits. If I do a logical AND, so AND the W register with a file register, that only updates 2 status bits, the 0 bit and the negative bit. And it kind of makes sense, because when you do logic, you don't usually think of overflows or carries. What we do think about is something 0 or is it negative. When you do a clear file register, that only updates the 0 bit. Guess what? It always sets the 0 bit to 1, because clearing a file register always results in making that file register 0, so it'll put a 1 in the 0 bit. So this table lists all the different instructions and which bits they update. And move file register will update both 0 and negative. And remember, when we say move file register, we can specify a destination. We can say comma 0, which says copy to the W register. But we could also say move file register, comma 1, which copies the file register to the file register. Why would you want to copy a file register to itself? Because in the process of doing that, the 0 bit and the negative bit get updated. So if you have a file register and you want to know if that register is equal to 0, move it into itself, and now the 0 bit's been set to tell you whether that was 0 or not. So you could do a branch of 0 somewhere, and that would change your program flow. move from one file register to another does not update any of the status bits. And that can be a big gotcha. You're doing this, you're checking the status, you're doing some conditional branch, and it doesn't seem to be working, and it makes no sense why. That's the reason why. So anytime you want to use the status bits, meaning anytime you want to do a conditional branch with branch of carry, branch of zero, and so on, make sure the instruction that you think you're using to check the result of, make sure it's updating the status that you're actually checking. Most of these make sense and you'll get the hang of them quickly, but there's a few odd ones like move FF that, why doesn't it update? Who knows? But what this means is, I could do something like this. So I'm going to decrement file register sum. I'm going to move FF sum into another file register called save sum. I'm going to say branch of zero done. The branch of zero is going to check the 0 bit. This does not touch the 0 bit. This is the last thing that touched the 0 bit. So this branch is going to be based on whether this decrement resulted in a 0 or not. So you can branch somewhere after the next instruction if you know that the intermediate instruction didn't change your status bits. Okay? And think of this from the processor's point of view, right? It sees a BZ, how does it know whether it should branch or not? Well, the easiest mechanism usually is it just has a status register. In BZ, it doesn't actually look at your previous instructions, it just checks the right bit in the status register. If you're saying branch of 0, it checks that 0 bit. If it's turned on, it branches. If not, it doesn't. To me, these conditional branches are a lot easier to work with than the skips. But like I say, I think that's just me. I think that's just because I'm old school. But you're welcome to use either. Bit operations don't change status bits. That's good to know. The branches themselves don't change the status bits. So you could do something like branch of 0, done, branch of negative, something else. All right, and this is checking the same status bits that were set in this decrement instruction because the conditional branch doesn't change them. So these conditional branches, there's a whole bunch of them. Branch of carry, negative, no carry, not negative, no overflow, not 0 overflow. Branch unconditionally and branch of 0. They blew 9 instructions just on conditional branches. They must be worth something to someone, right? Because that's, you know, like a fifth of the entire instruction set or something like that. That's not a fifth. But it's a big chunk of the types of instructions. All right, so questions on that?
So the difference between move F and move FF is essentially that one, like move F, the 0 and negative bit changes, but for move FF it doesn't change.
That's one big difference. The other big difference is move F takes a file register and either copies it to itself or copies it to W. Move FF takes one file register and copies it to any other file register, which could be itself, could be W, or it could be some totally unrelated file register.
Did I see a push and a pop?
There are. And we're going to drill into those eventually.
Cool.
And we'll do a lot with them. But yeah, there's a little stack inside here, and there's calls and returns,
Nice.
and we're going to use use those for interrupts, which will be a whole separate discussion. If you come down into the list of special function registers, pointed out before, I think, that register FE8, that's your W reg. It's just a special function register, like anything else. So I could do something like this. If I move F sum comma 0, that copies sum into the W reg. I could also do move FF sum comma W reg. It's going to do exactly the same thing. Why? Because this W reg is just another file register. It just happens to be one that a lot of instructions interact with. But it's just like any other register. All right, so questions about that? So let's think about coding some things. If x equals 7, go to blah, where blah is some label somewhere in the program. So we're writing pseudocode, we might get to a point where we want to test some variable x, see if it's 7, and if it is, go to some other section of our program. How would we go about trying to code this into assembly language? So we don't have any instructions that say see if x is equal to 7. Any ideas?
So for ours, we use the compare F SEQ.
Okay,
And so we took our first variable and moved it to the working register.
okay.
And then we did that command with our, well, in our case it was port B and our pass B.
Okay, so what are you putting in the working register?
So if you put like X in the working register, and then did a CPF SEQ with, well, I guess for us we were just comparing a different variable, but 7.
So the only problem with that is this is going to go after file register 7.
Right. Oh, yeah, so I think we stored the value. Oh, yeah, because it was comparing,
So how do we tell it we want the number 7 instead of file register 7? What's the buzzword I'm looking for?
Well, you put 7 in a variable and then use that variable to reference the 7.
Okay, how do we put 7 in a variable? Use a literal, that's the buzzword I'm looking for. So I can do move LW7. And compare file and skip if equal. This compares a file register to the W register. So since my W register is 7, I could just say compare file and skip if equal X. And this will say skip if X equals 7, because that's what's in the W register. So it's going to skip this instruction if X equals 7. If X is not equal to 7, it's going to do this instruction.
so then I think that's when we kept having branches. So we'd have a branch, if we needed reverse logic, we put a branch right under
Okay.
And then whatever we wanted the true condition to be, would be the next line. So if
Cool.
it failed the condition, it would branch somewhere else.
All right, good. So I could say here, branch, so if it's equal, it's going to skip this. So if it does this branch, it means x is not equal to 7. I'm going to say branch x is not 7. How's that for a legal name?